Hello, everybody. Welcome to our next round of Fellows Talks. Today we have Valerie, Andrii, Maxym, Andrii, and Mikola. So up first is Valerie. Valerie, whenever you're ready, go ahead and get started.
Yeah, okay, I'm ready. Yep, my topic is development of simulation workflow for beyond standard model long life particles at LHCb. My mentor is Aranza and Guren from IFIC, Valencia, Spain, and Bridge, Kishov Jahal, also from IFIC, Valencia, Spain. So about LHCb data flow, so Large Hadron Collider provides proton-proton collisions to LHCb 40 million times per second. So as a result of this, it generates a huge amount of data. It's approximately 5 terabytes every second. So we are not able to keep such data. So we are filtering it and trying to select interesting events. So data from detectors are filtered through trigger system, which consists two different high-level triggers, HLT, implemented in the software. So the latest update was about HLT1 level, Allen, which is implemented using GPU right now. About LHCb data simulation flow. So particle simulation is made by Gauss. Gauss also can be divided into generation, decay, propagation of particles. Yep. Then output of Gauss can be used in Boole for digitalization. So it just simulates the readout of detectors. So because not all detectors have output the same output, and some of them can not detect the particle even if particle flies through its physical volume. So then Boole output made such so it's the same as if it is real detector's output. So we can provide this information from Boole to trigger, which run by Moore. As also you can see in the slides, here in the left, it's also data from detector. So yep. And usually for analysis, we can use Gauss, Boole, and from Boole it can be used in DaVinci, which are used for Monte Carlo analysis, or in the Allen, which are HLT1 trigger, which run using GPU. So it's general definition of different LHCb frameworks, which I already described. So quickly about track type definition, because it's also important next. As you can see, there are two main different type of tracks. It's long track, a downstream track, and T-track. Upstream track is not so important for now. So for run 1 and run 2 conditions, only long tracks was available for some analysis. And now, because of Allen and GPU usage, we're also able to use downstream tracks for analysis. And also, we're expecting to be able to use T-tracks for analysis. Beyond standard model physics explanation, so we're also looking for some beyond standard model particles, and one of the simplest and well-known models is a mixed state between some scalar boson and the standard model Higgs boson, which regulated by mixing strength. And in the right side, you can see diagram how it can be found, and it describes the channel which we choose. It's B plus meson decay into the scalar, K plus meson. Then we are considering scalar which decay into muon muon, pine pine, or count count. Also, we are working with gluon gluon decays now. So here you can see branching. So the most important is that muon muon decay are probably still have high decay probability for all mass ranges. For mass range below 1 GeV, it's probably pine pine decay. From 1 GeV to 2 GeV, it's count count decay, and from 2 GeV, it's gluon gluon decays. So simulation of dark boson During work, we prepared official Monte Carlo samples for LHCb, which considered next mass range because of choosing channel, and also lifetime because now we are able to reach higher lifetime that was before. And we apply criteria like eta for scalar from 2 to 5. Eta is pseudo rapidity, special unit for LHCb. So here you can see configuration for official Monte Carlo samples, which was produced, and also we're working as was told on dark boson into gluon decay, which are important for dark mass, for high mass, sorry. So sensitivity studies, here you can see how signal amount depends on mass and lifetime of our scalar boson. And quickly about background source, because background source also really important, and we produced a lot of data for these studies. So about hadronic resonances, this hadronic resonances was very important in studies which was before. Strange particles, it's particles with long lifetime, so we can expect it in our zeta vertex region. As you can see, it's in the plot, so it has probably the same lifetimes as the regions that we discovered, and combinatorial background because of we also have a lot of tracks, or reconstruction algorithm can be ideal, so we're expecting some combinatorial and ghost background. Here quickly about muon decays, which are possible in minimum bias. So as you can see from the plot, that a major part of them located inside velo, and if muon decay produced inside velo, both of tracks will be long, and it will not have any effect on downstream analysis. Here we discovered a bit about hadronic resonances in downstream region. As you can see, it's from here is velo end. If particles run out of velo, it will become downstream track, or probably T track. So as you can see, mostly we can expect eta or ρ0 decays. Well, these particles can decay into muon, but they have low rate. So we're studying it right now, how it, which effect will it have on our search. About strange candidates, here you can see plot of reconstructed track categories as function of decay channel. So mostly all of these channels produce in the end car short or lambda. So all of them, as you can see, mostly have downstream and T tracks. So we also should use something to remove these lambdas and car shorts from our search. Selection procedure are made by neural network. As you can see, we make vertex and make pairing. So then we provide to neural network such information as both dot particles momentum and track quality, vertex quality and position, mass the particle momentum and quality. And in the end, we just need only one output, is like, is this pair is scalar boson decaying into muon or not? And here, as output from this neural network, you can see which combinatorial background do we expecting. So this was minimum bias sample, so it's probably just background sample, 100,000 events with neural network threshold 0.8. As you can see, it's low, so for 100,000 events. And we are still working with this. Maybe we will also add some improvements to this. So what we are planning to do next in our search for long life particles, beyond stellar model, now we are considering decaying into gluon because it can be used, for example, for HLT1 downstream jets recognition. And we're also interested in downstream hadronic resonances recognition because hadronic resonances can be produced from these gluons. Then we want to make this dark boson into muon-muon line implementation into HLT1, which is alien and neural network improvement. So that's all. Thanks for attention.
Thank you, Valerie. Any questions for Valerie? Nice talk, Valerie. Aranza, do you have anything you want to add to Valerie's presentation?
Yes, can you hear me?
Yeah.
I think Valerie has done really an excellent work. From the very beginning, he has been able to manage the simulations and the reconstruction of particles inside the LHCb. And his work has been already inside the LHCb, so people are able to use the Monte Carlo simulations that he has been generated in a large sample. So it is something that it is going to be very important for the collaboration for the future for searches. So I think it has been an amazing work. I'm really happy about all of what he has been doing.
Great, thank you. Andrii with P, you're up next.
Okay, hi everyone. My name is Andrii Povsten, and my project involves developing a Snakemake backend for RECAST with guidance from mentors Matthew Weichert from University of Wisconsin-Madison and Lucas Heinrich from Technical University of Munich. I think the good place to start is to briefly explain what is the reproducible analysis and why do we need it. According to the Nature magazine, shockingly, but over 70% of researchers have faced difficulties in reproducing another scientific experiments, and like half of them, they can't even reproduce their own research papers. And these challenges spark discussions among thousands of scientists, but but at least half of them believe that they're published, they still place trust in published literature. And in fields like psychology or cancer biology, some famous studies had low rates of being repeated successfully, around 40% and 10%. So reproducibility in research means that it's being able to redo and confirm scientific experiments and data analysis. So it's reproducibility ensures the integrity of your research. It's like when your analysis is reproducible, it's easier for others to validate your findings and build upon your work. And reproducible workloads, they save time. You won't need to redo your analysis from scratch every time. You just make a change or need to run an experiment. And a well-structured workflow explains the order of tasks, the code used, and the inputs, outputs, making the whole process transparent and easy to check. And also a lot of private companies, which is like make like investment in research. They expect that this research you can reproduce like later. So now it's really like important question to my mind. And for such purpose, RECAST was created. It's the main part is the possibility of reusing and running the workflows. So the RECAST is a framework for extending the impact of existing analysis performed by high-energy physics experiments. And this framework allows scientists to access and reuse workflows that have already been performed. So this way, scientists, they don't have to re-estimate the standard model backgrounds each time, saving a lot of time. And they just, instead, the only thing they need to do is just to run the statistical analysis to see if the new model is supported or not, and figure out how the new physics model fits into the experiment space by running the event selection code in like some samples. Okay, but what is the workflow language? Like workflow language is a way to describe an organized series of tasks or steps that need to be performed in logical order. I like this comparison with cooking recipe. I like creating a recipe for a cooking process, or just set instructions for building some Lego blocks, you know. So yeah, there's like now more than 100 workflow languages, but the most popular of them is like Common Workflow Language and LHCb, which I will take a bit later, and Snakemake, also very popular nowadays. And about LHCb, previously the RECAST used the LH workflow language, which was created by Lucas Heinrich. Actually, it was born out of necessity because at the time RECAST was implemented, there wasn't any workflow language with mature Linux implementation. But LH can deal with it, with such challenges, because instead of describing a specific graph of tasks, LH consists of the stages, like and nodes, like so. Like you have a body, which is scheduler, which describes of logic how to define new nodes, and which is like some inputs or like activities, and new edge to attach them to the existing graph. This depends on the JSON path expressions, as you can see in this small example. But now Snakemake is evolved. I just quickly tell what is it, and can be implemented. Snakemake is like really powerful tool for creating reproducible and scalable analysis. As it says, it's like framework for reproducible analysis. And why our motivation to use Snakemake? It's Python-based workflow management system, so it's really easy to understand it and read for only for physicists or for programmers, just for normal people. Yes, and Snakemake integrates seamlessly with Cond and Package Manager and the container engine Singularity 11, that you can define the software stack within the workflow. And just to quickly tell the Snakemake, you need to create a snake file, which is similar as a function to a make file. Each step in the workflow is defined as a rule. I will show the code a bit later, but you can imagine as a rule, and where you have like outline input files, output files, and the shell command or Python script. Yes, but for a run like Snakemake workflow, you need to create like environment file, environment definition file, which all software requirements. Conda, Mamba, Micromamba, they typically use an environment YAML file. So we have created the environment file for Atlas workflows, RECAST Atlas workflows, and this environment files, they contain all necessary packages and requirements for running Snakemake workflows. This is just for RECAST dependencies, and for Rihanna, which I will talk a bit later, but you can imagine it like this, just two separate files. Yes, so, and also in the repository Snakemake backend RECAST, we provided introduction, just a screen of one of this. I think it's quite clear. We didn't try it for another users, but I think it's quite clear to see instruction of how to run the Snakemake workflows. Yeah, so like the main part was to create the snake file, which is like run the workflows, and as you can see, which has like rules for the execution. Like in this case, you have like you can specify the conda environment, you can specify the even container, yeah, and this is like the final rule, which is like have the, as you can see, final output with hello world output, but like prepare data rule, it basically creates the file with our case like hello world with like shell commands. Then we have like an example file and output results that you create. Like firstly, I will show you later. You can see that it's firstly create the file, and then we put this file into from one direction to another one. Yeah, and log files. As you can see, this like I think it's a really cool feature, the log files, because you can see like the whole process of building your workflow. As you can see, you have like you can see what using shell, which is now its conda environments and containers are ignored, but you can see your final conda environment and your container environment. Yes, and all the steps. So if something is broke, it's easily to see, or like when something goes wrong, you know. Yes, and also we implement the continuous integration using GitHub Actions. I think it's like really important practice, because CI involves running tests and checks after each code commit, catching potential issues early in the development process. Yeah, and the nice part about Snakemake that it provides own action for continuous integration, like logs, as I mentioned previously, and linting, which is one of the also cool features, since it shows you the like the linting, like it checks your snake file and even config file, which gives you information like how to better improve your workflow by adding some containers and in some virtual environments, or just checking is it any errors with syntax. And yeah, and also we, like, after running all this snake file workflow, we try to implement it on the Rihanna cluster. Rihanna is a reusable and reproducible research data analysis platform, which helps to structure your input data, analysis code, and workflow. So, so our workflow also running on the Rihanna. It provides the necessary computational resources such as CPU, memory, and storage to, like, you can execute and monitor your workflow directly on the web pages like rihanna.th. Yes, and like in conclusion, I just would like to say that Snakemake is really, like, in comparison to Yedich and CWL, I think it's really easy in use and to debug workflow language, provides a lot of different opportunities. And now, after like running this example, we clearly see that Snakemake can be implemented for RECAST for like more complex analysis, which is more complex analysis, which is like the main feature, which can be easily done by looking at the instructions and log files and hello world snake file. Yes, and Thank you for your talk.
Next up is Maxym.
My name is Maxym, and this is a presentation for the project of applying machine learning for network problem identification, which I've been working on with my mentors, Snakemake and Valerii. First of all, a little introduction. Large Hadron Collider generates petabytes of data every year, and we want to be able to access this data not only from being directly on site, but from our home institutions throughout the world. And for this reason was created a network, which you can see on the screen. The LHC itself is on the bottom right. Here is Europe cluster. Here, middle top is North America, and the bottom is South America, and on the left is the Asia region. So what if we, for example, want to get some data from LHC and we are having low throughput or can't load the data at all? It means that something in this network on the way to us is broken or having some troubles. So to find to identify these problems, such a device was created called PerfStar, which is installed on every site and measures its performance throughout the time and stores it later in a platform called Elasticsearch. Here there are separate lots of separate scopes for different data. For example, for packet loss measurements, for throughput measurements. Here you can see the scope for throughput, and here for the period of time I've chosen, there are 30,000 measurements, and for this hour there are 730 measurements. Each measurement consists of data of the names of the source site which we are sending, which we are at, and the destination site, and also some useful information. Among them is the throughput value itself. We'll talk about it a bit later. So with this data that we're having now, we can run some automatic alarms for throughput. For example, when for a specific site it drops below a certain threshold, and we have such alarms right now, and we'll be using it later to mark the data sets for our machine learning models. And we are slowly getting to the next part, is network problem identification using ML for throughput measurements. On the left here, you can see the data sets more specifically, which we are getting from the Elasticsearch. You can see here some useful information of when the measurement was taken. Here it is already converted to a timestamp. If the connection is an IPv6 or IPv4, the value for the throughput itself, and the names of the source site, destination sites, and hosts' names. And if there was created an automatic alarm for this measurement. The data that was taken was from the 1st of January till the end of May, and we are getting about 500,000 measurements for this period of time. So to use this, before we can use this for machine learning, we have to convert all the categorical data, meaning the names of the sites, to the numerical data. For that, we can use the one-hot encoding algorithm, which basically will create a a new row for each of the site names and put ones if the measurement was taken for that site and zeros otherwise. And on the right, you can see already changed data set with only numerical values, and we can use it for machine learning. So on the left here is the results for the trained HG boost model with accuracy. We got the accuracy of 98%, which is nice. But if we look at the confusion matrix, we can see that we have highly unbalanced data, meaning that we have lots of measurements and only a small amount from them are actually faulty. And to maximize this number, when the model predicts faulty measurements, we will use the random hyperparameter search and we'll be maximizing the F1 short, which is actually developed for that kind of reason, to maximize the values on this diagonal. And after applying it and using the hyperparameters from it, we can see the slight increase in accuracy and increase in F1 short, and we can see that the number here of correctly predicted values increased. So let's look at the data itself, and for that we'll take only one site. Here is a Taiwan site in the period of time when we know there was a problem occurring for that site. On this plot, you can see on the x-axis the time when was measurement taken, and on the y-axis the throughput measured for it. And the red dots are the alarms which were given from the ML model. And we can see clearly that the throughput here greatly decreased. We can look at another plot of the number of the alarms aggregated daily, and the number of the alarms for this period of time increased also significantly. So to not look through all the sites in our data and look for sites which have some visible problems, was created an algorithm that looks through each and every site and creates an alarm if there is a high increase in the number of alarms through a couple of consecutive days. And after running that algorithm for our data set, which I remind is taken from the period of time from the 1st of January till the end of May, we got about 22 unique alarms for the sites, which had problems for a period of time from 3 to 14 days. And here we can already see that our Taiwan issue got classified correctly. And there are actually 3 types of alarms you can see here. The first type is false alarm. For that sites that actually very good have very good performance, and the mere occurrence of alarms stands out from the all-time graph. Examples are the Yuki site and the BA grid. Here you can see the plots for them. As you can see, no problems on the throughput plot, and alarms, we can see that very low number of alarms over that period of time. The second type of alarm is when we have major problem classified, and we can visibly see it. The examples are Taiwan, for example, and US CMS, yes, or Vanderbilt, more correctly. You can also see here that there was some kind of alarm, and and the algorithm classified it correctly. We have the high decrease in alarms and visible decrease in throughput. And the last type of alarm is when we can't actually see it on the plot where the site is both a destination and a source. Also, there is a high increase in alarms, in the number of alarms. It means that the problem may be occurring not directly on the site, but somewhere on the way. And to see more clearly where it happens, we can look at the plots where the site is destination only. There's no problems for it. But if there were, it means that there was some problems near it on the optic cable, for example. And if you look at the plot where it is a source only, we can see that the problems, there is some problem with this type exactly. And it means that while trying to connect from it to some sites, somewhere near it also, there is some problems. There may be different problems from bad optics, bad nodes on the way, or just bad electronics from the device it's measuring it. We can say for sure, but to narrow down it more, we can see at all of the source destination pairs where this site was a source for this period of time, and probably for this first sites with the higher number of connections, somewhere on the way to them there is a node and it's faulty. So let's get to the other type of alarms, packet loss alarms. I won't be going through all the points from the throughput analysis, and we'll jump straight to the results. The period of time is the same from the beginning of January till the end of May. And here we can see also that there was an alarm for Taiwan site and for the US CMS site, which were seeing at just now. But here comes the interesting thing that we'd expect the correlation between the low throughput and high packet loss. So if we have low throughput on measurements, then we'd expect high packet loss, and vice versa. But instead, we have some cases when, for example, this is a Taiwan issue, which we have problems both in packet loss alarms and throughput alarms. You can see that the increase in the alarms. But if you see, for example, for the Vanderbilt site, we had a clearly visible decrease in throughput, but for packet loss, there's only a little increase in alarms at one day at the end of January. And the other example is for CIT CMS site, when we are having some troubles visible for packet loss measurements, but we haven't been seeing it for throughput measurements. So this is an interesting thing, and we can explore it more later. Finally, I'd like to show you the Plotly Dash page that was created to for other researchers to be able to recreate the results I got, and not to go through the Python files or Python or Jupyter notebooks. Here it is. We can choose a period of time for when we want to change the model, choose an alarm time type. We'll get the list of alarms for this period of time, and we can then, for example, choose a site which we want For example, at Taiwan, we know that there was an issue in, and get different plots for the site where it's both a source and destination, some description, and when it's a source only and destination only, and to choose also both source and destination. This is currently working. This is currently running locally on my PC, but later we will deploy it on server to the Dash platform that already exists with automatic alarms, and you will be able to play around with the data yourself. The link for it will be at the end of the presentation here. Here. And finally, conclusions. In this project, we first created suitable data sets using different techniques such as one-hot encoding, using this data fetched from the Elasticsearch platform. Then using these data sets, we created our own alarms using machine learning, and this way we explored two Elasticsearch scopes with the throughput and packet loss measurements, and while comparing them, the results from both, instead of expected correlation between high packet loss and low throughput, we had some cases where it wasn't present, and it's an interesting topic to explore further on. So that would be all. Thank you for attention.
Thank you, Maxym. Nice talk. Petya, you were one of his mentors. Do you have anything you want to add to Maxym's talk?
Hi. So I just want to say that he did a really good job, and he made our data much more useful with his work. He's very smart and capable, so I would like to thank him for his work.
Thank you, Petya.
Great. Nice talk, Maxym. Next up, Andrii.
Hello, my name is Andrii. I want to present the project named Predict CMS Data Popularity to improve its availability for physics analysis. My mentors were Dmytro Kovalsky from MIT and Rahul Chauhan and Hazan Ozturk from CERN. So, the CMS data management team is responsible for distributing data among various computing centers globally. However, due to limited disk space at these centers, it becomes necessary to dynamically manage the data availability on disk. This disk, which is also called cache. When the data is not readily available on disk, users have to wait for it to be retrieved from permanent tape storage, causing delays in data analysis and hindering scientific productivity. The basic question we are trying to answer in the study is which file we can delete from the cache. To answer this question, we collected historical data of data usage, found and explored the parameters by which we can establish the popularity of data, tried different architectures of machine learning models, and optimized the best one. Historical usage data we extracted from CRAP database using Spark. CRAP stands for CMS Remote Analysis Builder, where we stored a lot of various information about files usage. All in all, we gathered 3 years of data. When a data set is accessed by a user, the so-called task is created. It contains information about when the data set was accessed, by whom, and a lot of other parameters. The example of the data set that can be accessed, you can see lower on the slide. The name itself contains a lot of useful information, like primary data set, acquisition era, and data tier. We tried different features and their combinations, and after such a research, we came up with optimal set of features, which you can see on this slide. But the problem was that we have both text and numerical features, so we needed to preprocess them accordingly in order to use them in our models. For text features, we use tokenizer, which creates a dictionary of elements and turns a string into a vector of numbers. Also, I implemented embedding layers, which are used to map discrete tokens or integers into a continuous vector space. They are an additional layers in a machine learning model that learn alongside with main layers and allows the model to capture semantic relationships between tokens, which is extremely useful if we have meaningful context in our strings. After this preprocessing, in order to add some time component in our training, we added used or not feature, which describes if the data set was used in the previous months or not. Also, we found out that the information about how many different users used a particular file is also useful. All machine learning was done on Python using TensorFlow and Keras libraries. The model, the best model consists of 5 input layers, 1 for every feature, 2 embedding and flatten layers for text features, 3 dense inner layers with a reluctant activation function, and the output layer, which gives us a single number for binary classification. Binary classification approach allows us to receive values between 0 and 1, which can be interpreted as probability of datasets future usage. And it's exactly what we need. All details corresponding to gathering data, preprocessing, training, and evaluation could be seen on our GitLab repository in few days. So after training, we should evaluate the results. We used some widely known metrics for machine learning as precision, recall, and F1 score, which are calculated from confusion metrics, which you can see here. But especially for our current task, we created another matrix, which allows us to estimate model's performance. Here, I want to mention that the most trivial information in our studies is if a dataset was used recently, it will be used in the nearest future with high probability. That's why we are looking on how many datasets which were used or not in previous months are correctly predicted for the current months, which is our target. The glance on such a table gives us a hint on which group of datasets is predicted badly and which feature or which representation of some feature we can use to improve training. After creating an appropriate model, we needed to compare it with a current algorithm for caching. This algorithm is least recently used. The idea of LRU is that if we need to create some space in cache for new incoming dataset, we simply evict the least recently used dataset. This approach is very simple and quite effective for such tasks. And on the other hand, when we do caching with model, we evict the dataset with the lowest predicted probability. In the end, we created a real caching simulation to compare least recently used and model approaches. The idea of simulation is if the incoming dataset is in cache, we call it hit and store this event as true or 1. If dataset is not in cache, we call it miss, put this dataset in cache while deleting some other dataset. which one dataset to delete is decided based on specific algorithm, LRU or model, and store such event as false or zero. Average hit rate comparison we can see on the plots. So after trying different cache sizes and different time periods, the comparison of least recently used algorithm and our model allows us to conclude that our model with constant retraining slightly outperforms LRU. In conclusion, I want to say that it was extensive research, but despite that our model performs better than LRU, taking into account its simplicity, LRU is a better choice for the data caching, at least for now. More work is needed to explore full potential of this approach and use all power of historical data in training. That's all. And in the end, I also want to say thank you to my mentors for their guidance and regular assistance. It was a great pleasure working together. Thank you for your attention.
Thank you, Andrii. I see all three of your mentors are connected with Rahul or Dimitro or Hassan. Like to say anything?
Yeah, maybe I'll say a few words. So I would like to thank Andrii for all his hard work. This was a real R&D study, so it was pretty challenging. We were more or less just giving him general directions, and then he would need to go and figure out everything, how to make it work. And this was a lot of work, extracting data, building models, coming up with new ideas, how to do that. So I think that was a very interesting project for us, and I hope he learned a lot as well. And thank you guys for giving us this opportunity to do that. So.
Great. We're happy to hear when it's a successful collaboration between you and the student. So that was, thank you. Next up is Mykola.
I am Valerii Kholoimov from Taras Shevchenko National University of Kyiv. My mentors are Dmitro Kovalsky, German Giraldo, and Jen Eisermans. And the theme of my project is improving testing procedure for tier 0. So a little bit about tier 0. Its responsibilities are workflow configuration, output data placement, prompt data reconstruction, and it also bookkeeps the most sensitive data in the CMX experiment. So we don't want any data loss, and the thing that can cause this data loss are errors in the software. So we do want to have a good tracking system for these errors. For that we have before my project there were existing some tests. It's Python syntax tests and replay test. There are also some unit tests that were outdated, and the problem was that Python syntax tests are very basic and also don't detect any real problems with software. And replay test is very large, very difficult to process, so requires much computing power. And when you develop something, you should run a replay test before these changes goes to production. So you should wait until the replay test is finished and then see the result, and then your changes will go to production. And we want to have something between those tests, like like unit tests, small unit tests, or smaller replay test. And at first I wanted to reuse these old outdated unit tests, but there were some problems with them and it didn't work out. So the new plan was to add new unit tests that can help to refactor the code safer and easier and detect these problems before running replay tests, so we can change something that errors go away and doesn't require running replay tests and waiting for some time. Also, you can see we don't lose as much time or computing power to run this replay test for nothing. And also, we added an option to limit data injection, so replay test doesn't require so much computing power and less time. And you can see the results much earlier. And also we adding an option to run replay locally. Basically, tier 0 uses a thing called htconder, and the way we run replay locally is we change universe of htconder. It's an option to use for htconder, so that it runs jobs locally and don't run it in any other machine. So that's the way we do it. That's my project. Very quick presentation. Any questions?
Any questions for Mikola? Oh, we have a hand raised. Herman?
Hi, can you hear me?
Yep.
Yeah, not just to mention that we are very grateful with Mikola for the job that he did with us. This presentation, I think, he is very humble in presenting his achievements, but actually what he did, reducing the complexity of our especially of our replay test, is something that's going to save us a lot of work and a lot of time waiting for results, and it's going to allow us to be more efficient. And he did a lot of investigation on different ways to implement these changes, and he had to go into the system and try to really understand how to make these changes in the best way. And so thank you, Mikola, for all that effort, and we're already reaping the benefits of it. So thanks again.
Oh, it's nice to hear. So, any other questions? No. All right. Thank you all for coming. Thank you to the fellows for your presentations. Thank you for the mentors for showing up and mentoring the fellows through the process. That's all we have for today. So thank you all.
Thank you. Goodbye.
Thanks. Bye.
Thanks. Goodbye.